Black holes are among the most fascinating objects in the universe. These mysterious entities have captured the imagination of scientists and the public alike for decades. Their very nature challenges our understanding of physics and the fabric of reality itself. They are regions of space-time where gravity is so strong that nothing, not even light, can escape. This immense gravitational pull is a result of a massive amount of matter being compressed into a very small area, creating a point of infinite density known as a singularity. Imagine a place where the fabric of reality itself is distorted and time comes to a standstill. This is what happens near a black hole. The closer you get to the singularity, the more extreme these distortions become, to the point where the laws of physics as we know them cease to apply. These cosmic abysses are not just theoretical constructs. They are real entities that have been observed and studied by scientists for decades. With the advent of advanced telescopes and observational technology, we have been able to capture images and gather data that provide insights into these enigmatic objects. Black holes are formed when massive stars collapse at the end of their lives. This process often involves a supernova explosion, where the outer layers of the star are ejected into space, leaving behind a dense core. If this core is massive enough, it will continue to collapse under its own gravity, eventually forming a black hole. The immense gravitational pull of these collapsed stars creates a region of space-time from which escape is impossible. This region is bounded by what is known as the event horizon, a point of no return beyond which nothing can escape the black hole's grasp. Anything that crosses the boundary of a black hole, known as the event horizon, is forever trapped within its grasp. This includes not just matter, but also light and any form of radiation. Once something crosses this threshold, it is doomed to spiral inward towards the singularity. Black holes are not cosmic vacuum cleaners, as they are often portrayed in science fiction. They do not roam the universe indiscriminately, sucking in everything in their path. Instead, they exert gravitational forces just like any other massive object. They do not suck in everything around them. Objects can orbit a black hole safely, just like planets orbit stars. In fact, many black holes have stars and other celestial objects in stable orbits around them, forming complex systems that can be studied to learn more about the nature of these fascinating entities. Objects can orbit a black hole safely, just like planets orbit stars. These orbits can be stable and long-lasting, allowing scientists to observe and study the interactions between black holes and their surrounding environments. Only when an object crosses the event horizon does it become doomed to fall into the black hole's singularity. This journey towards the singularity is a one-way trip, where the object will be stretched and compressed by the intense gravitational forces, a process known as spaghettification. The study of black holes is a testament to the power of human curiosity and the ingenuity of scientific exploration. Researchers use a variety of methods, from theoretical models to observational data, to unravel the mysteries of these cosmic phenomena. They challenge our understanding of the universe and push the boundaries of our knowledge. Black holes force us to rethink the fundamental principles of physics, from the nature of gravity to the behavior of time and space. In the vast expanse of the cosmos, black holes stand as enigmatic sentinels, guarding secrets yet to be unveiled. They are a reminder of the incredible complexity and wonder of the universe, and they continue to inspire scientists and enthusiasts alike to explore the unknown. Stars are born from clouds of gas and dust, known as nebulae, which are vast regions in space filled with these primordial materials. These nebulae are often the remnants of previous generations of stars, containing the elements necessary for new star formation. Under the influence of gravity, these clouds of gas and dust begin to collapse inward, pulling the material closer together. As the particles draw nearer, the temperature and pressure at the core of the collapsing cloud increase dramatically. The intense pressure and temperature at the core of a star ignite nuclear fusion, a process where hydrogen atoms combine to form helium, releasing a tremendous amount of energy. This energy powers the star, causing it to shine brightly for millions or even billions of years, depending on its mass. However, even the most massive stars have a finite lifespan. Over time, they burn through their nuclear fuel, converting hydrogen into helium and then into heavier elements like carbon and oxygen. As a star exhausts its nuclear fuel, it can no longer support its own weight. The outward pressure from nuclear fusion diminishes and the star begins to contract under its own gravity. The core collapses inward, while the outer layers are expelled into space in a spectacular explosion known as a supernova. This explosion is one of the most energetic events in the universe, briefly outshining entire galaxies. If the core of the star is massive enough, the gravitational collapse will continue indefinitely, forming a black hole. This process compresses the core's mass into an incredibly small and dense point known as a singularity. The exact threshold mass for a star to collapse into a black hole is still a subject of ongoing research. Scientists use advanced models and simulations to understand the complex physics involved in this transformation. However, it is estimated that a star needs to be at least 3 times more massive than our Sun to form a black hole through stellar collapse. Stars of this size undergo more dramatic and violent ends compared to smaller stars. Black holes formed from stellar collapse are relatively small, typically with a few times the mass of our Sun. Despite their size, their gravitational pull is so strong that not even light can escape from them. However, they are incredibly dense, packing all that mass into a region just a few kilometers across. This density creates a gravitational field so intense that it warps the very fabric of space-time. The density of a black hole is so high that it warps the fabric of space-time around it, creating a region known as the event horizon. This is the point beyond which nothing can return once it is crossed. The bizarre effects that black holes create, such as time dilation and gravitational lensing, make them one of the most fascinating phenomena in the universe. These effects challenge our understanding of physics and continue to be a major focus of scientific research. The event horizon is the defining feature of a black hole. It represents the boundary in space-time beyond which the gravitational pull becomes so overwhelming that escape is impossible. This boundary is not a physical surface, but rather an invisible threshold. Once crossed, the escape velocity exceeds the speed of light, making it impossible for any form of matter or radiation to break free. It is the boundary in space-time beyond which gravity is so strong that nothing, not even light, can escape. This phenomenon is a direct consequence of the warping of space-time caused by the immense mass of the black hole. The closer you get to the event horizon, the more pronounced these effects become, leading to extreme gravitational lensing where light paths are bent around the black hole. Once an object crosses the event horizon, it is destined to fall into the black hole's singularity. This journey is inevitable and irreversible. The object will experience a process known as spaghettification, where the gravitational forces stretch it into a long, thin shape. This is due to the difference in gravitational pull between the part of the object closer to the black hole and the part further away. The singularity is the point at the center of a black hole where all the matter is concentrated. It is a region of infinite density where the known laws of physics cease to function. The concept of a singularity challenges our understanding of the universe, as it represents a point where our current theories of gravity and quantum mechanics break down. It is a point of infinite density and zero volume, where the laws of physics as we know them break down. At the singularity, the curvature of space-time becomes infinite, and the gravitational forces are infinitely strong. This creates a paradox where the equations of general relativity no longer provide a meaningful description of the phenomena occurring at this point. The nature of the singularity is one of the biggest mysteries in modern physics. Scientists and researchers are continually exploring new theories and models to understand what happens at the singularity. Some propose that a theory of quantum gravity, which unifies general relativity and quantum mechanics, might provide answers. However, such a theory remains elusive. Imagine you are falling into a black hole. As you approach the event horizon, the effects of gravity become more extreme. You would experience time dilation, where time appears to slow down relative to an observer far away. This is a consequence of the intense gravitational field affecting the passage of time. As you approach the event horizon, time would seem to slow down for you relative to an observer far away. This effect becomes more pronounced the closer you get to the event horizon. To an outside observer, it would appear as though you are moving slower and slower, eventually seeming to freeze in time as you reach the event horizon. From the observer's perspective, you would appear to freeze in time at the event horizon. This is because the light from you takes longer and longer to escape the gravitational pull of the black hole, making it seem as though you are suspended in time. However, from your perspective, time would continue to flow normally. You would continue to fall inward, eventually reaching the singularity in a finite amount of time. The journey to the singularity would be a one-way trip, with the gravitational forces becoming increasingly stronger as you get closer. The experience would be unlike anything we can imagine, as the laws of physics as we know them no longer apply. The event horizon and singularity are concepts predicted by Einstein's theory of general relativity. This theory describes how massive objects warp space-time, leading to the formation of black holes. The predictions made by general relativity have been confirmed by numerous observations and experiments, solidifying our understanding of these cosmic phenomena. While we have not yet been able to directly observe the singularity of a black hole, there is overwhelming evidence for the existence of event horizons. Observations of stars orbiting invisible objects, gravitational waves from black hole mergers, and the recent imaging of a black hole's shadow all provide compelling evidence for the existence of these fascinating and mysterious objects in our universe. One of the most intriguing consequences of a black hole's extreme gravity is the phenomenon of spaghettification. This occurs due to the difference in gravitational pull across an object's length as it approaches the black hole. Imagine a spaceship falling into a black hole feet first. The gravitational force at the ship's base would be much stronger than at its nose. This difference in force would stretch the spaceship like spaghetti, eventually tearing it apart. The closer an object gets to a black hole, the more pronounced the spaghettification effect becomes. This is because the gravitational gradient, or the rate at which gravity changes with distance, becomes increasingly steeper. For a small black hole, the tidal forces would be strong enough to spaghettify a human even before they reach the event horizon. While spaghettification may seem like a gruesome way to go, it is a fascinating example of the extreme physics at play near a black hole. It highlights the immense power of gravity and the strange effects it can have on matter.